Hello everyone, welcome once again to our Lee County Library Science Club. It's great to have you back. I just want to remind everybody, all of our experiments carry a small amount of risk, so please make sure you have your parents' permission and some supervision when you're trying these out. This week, we are going to use our minds to make water float in the air. Now, our minds are going to be using science to accomplish this, but it's still going to happen. You ready? So, the concept that we are using to make this happen is a combination of air pressure and surface tension. Now, air pressure is the way air pushes against objects around it. So right now, in this room, the air molecules are all being pulled down by gravity. But, obviously, there's a floor here, right? So those air molecules can't keep going down. They're hitting against the floor. And according to Newton's third law of physics, every action has an equal and opposite reaction. So if those air molecules are being pulled down against the floor, then at the same time, they have to be pushing back up against whatever else is around them. Normally, air moves very easily. So if it's pushing against an object, well, it's just going to go right around that object, right? But if you don't give it any other path around an object, it will push against it and hold it in place. Normal sea level air pressure is roughly 15 pounds per square inch, which is kind of a lot, but it's still less than solids or liquids would have. But the air around us definitely has some weight to it. One thing that's created by gravity pulling on this air is that it tries to create an equilibrium or a balance. So I have a jar here that has air inside of it, right? But if I were somehow able to make there be less air inside the jar than there is outside the jar, well, because of the air pressure around it, the air would try to rush in and create a balance again. But if I pull the air out and then seal it so that the air can't get back in, well, there's still an imbalance there. So the air is still going to be pushing against this, even though it can't get past it. It's going to be pushing whatever is against whatever is making that seal, and it's going to hold it in there. Now our second concept that's important today is surface tension, which is the tendency of liquids to try to minimize their surface area and hold together as much as possible. And this is created by a property known as cohesion. Cohesion simply means particles of the same substance sticking together. Now the opposite of that is adhesion, where you have particles of different substances sticking together. But what we're going to be mostly focusing on today is the cohesion. And one of the causes of cohesion is polar molecules. And so the water that we're going to be using today is pretty special in that it is a very polar molecule. And I know we've talked about that before a little bit, but I wanted to show you a little more clearly what it means that water is a polar molecule. This little ball model here is sort of what a water molecule looks like on the atomic scale. It has one larger oxygen atom and two smaller hydrogen atoms bonded to it in this shape where there's kind of like, looks like little legs, right? Now, as we've said before, hydrogen atoms have an electron that doesn't really like to stay around the hydrogen atom, okay? Because there's only one proton in there, and there's just not a strong connection between that electron and the nucleus of this atom. So when a water molecule forms, the electrons that normally fly around this hydrogen atom start flying around both the hydrogen and the oxygen atom. But because there's more protons here, and it's a larger mass here, that electron spends more time flying around the oxygen atom than it does the hydrogen atom. So, if there are more electrons spending more time around this atom, what ends up happening? Well, it creates a negative charge around this side of the molecule, and a positive charge around this side of the molecule. Okay? So every water molecule has a negative side and a positive side. So then what happens if you have several water molecules near each other? Well, like we talked about in the electromagnetism topic, a negative side and a positive side will be attracted to each other, right? So water molecules tend to line up in shapes like this, and they are very attracted to each other. And this creates cohesion, okay? These molecules don't want to pull away from each other. There's actually a pretty strong force keeping them together, and that gives us surface tension. So today we're going to be using the air pressure in the room pushing against the objects and the surface tension of the water to hold water up in our jar without it falling down. What you'll need is a mason jar. The one I have here is a quart jar with a wide mouth, but you can definitely use a smaller one like a pint jar, and I would actually recommend one with a regular size mouth just so that it's easier to cover. Okay? Now, part of the key to this is that you need the lid that has two parts to it, so that you can take out that middle part and just have the ring that screws onto the outside of the top. Okay? Then you need some mesh screen. Okay, make sure it's metal or plastic. This is just screen door or window screen that you can get from a hardware store or Walmart or even a hobby shop maybe. You'll need a card. I have a laminated index card here, but you can use something like a playing card or a coaster, just something that's wide enough to cover the opening of your jar and is also just kind of light. Okay? Now, you'll probably want a nice big bowl just in case we make a mistake. Your mom probably doesn't want the water splashing all over the floor, right? So have a bowl to catch it just in case. And then, of course, we need some water. Also, you may want some towels on hand just in case. So the first thing we're going to do is put the wire mesh over the jar and kind of pull it down so that it's stretched tightly over the top of the jar. Then we are going to screw the ring of the lid onto the jar. Now this may take a little bit of trial and error because it is kind of hard to screw it on with the wire in the way. Now once you've got your mesh tightly on there, you can actually take some scissors, not your mother's nice sewing scissors, some other older ones maybe, okay? And you can cut it right around the rim of your bottle, and this way you can actually hide that screen from people. Okay? So now, if you look at it quickly, it just looks like a jar with an opening. Okay? Now, to start our experiment, we want to fill the jar at least halfway up. You can do more than that if you want to, but we want to make sure we have a good, substantial amount of water in there. Okay? Now the next step is to place the card over the lid. You just want to make sure that there's no openings, okay, no way for the water to get past that card. Then you're going to pick it up, hold it on there, okay, and flip it. Now when you flip it, there may be a little bit of water that splashes out or moves, but that's okay. Just make sure you get it pressed up against it, okay, and then you can take your hand off and look at that. The card stays stuck to it. So this is showing us how the air pressure, okay, because the air is trying to get past that water and fill up the jar, it's pushing against the index card and holding it in place. Now, before we go to the next step, I just want to demonstrate why this air pressure is actually working, okay? So we talked about before that the air at sea level, air pressure is about 15 pounds per square inch, specifically 14.7. So if we were to put the jar on the card, okay, we can outline it. Alright, that gives us a rough estimate of what our circle looks like. Okay. Now I have here, this bar is about 1 square inch. So if I put it inside our circle, there's 1 square inch, and there's 5. Okay? So that means we have at least 5 square inches being pushed against by our air pressure. So if it's 15 pounds per square inch times 5, that's almost 75 pounds of pressure pushing against this card. Now, our water is about 8 pounds per gallon. So if you've put maybe 2 cups in here, okay, then we're going to end up with about 2 pounds of water in our jar. 2 pounds of water pushing against almost 75 pounds of air pressure is what keeps that index card up on that lid. Now I know we still haven't really made this water float yet, have we? So we go back, start the same way we did before, okay? Try to seal up the top of our jar. Then we're going to flip, okay, keeping the water inside the jar as much as we can. And again, that index card is stuck there, right? But this time, we're going to gently remove the index card. Now you might have a little bit of water come out if you didn't have a good seal when you flipped it. But now, you can see the water is floating up in this jar, right? There's nothing below it, nothing holding it up. Okay, it's just the water. Now how is that happening? As we talked about, it is the surface tension, right? Because the mesh makes the pockets of air there small enough that the air, as it tries to push through those pockets, can't break the surface tension that is created by the water in between those mesh openings. Okay? The water has a strong enough cohesive force that's strong enough to fight against both gravity and the air pressure that are trying to make the water come out. Okay? But this only works as long as we keep that surface tension together. If you do something to break the surface tension, like shake the jar, the whole thing comes apart. Ready? 3, 2, 1. Oh! See there? It all came down. Now, surface tension and air pressure and water pressure can be pretty important concepts in our modern world, If you've ever heard of hydraulics, like some of you have hydraulic brakes in your car, or if you ride on a school bus, they have air brakes in their car. They use air pressure to actually slow down the bus. Okay? So this concept of air and water pushing and having forces in them is what allows a lot of those types of machinery to work. Thank you so much for coming. I hope you enjoy it. We'll see you next time. Bye.